Chapter 20. Many electron atoms. Section 20.8. Atomic term symbols for the D2 electron configuration. The total number of microstates is 10 times 9 over 2 factorial, which is 45 for the D2 electron configuration. This is because when we place the first electron in the 5 different d orbitals, there are 10 options. The second electron has 9 options. 10 times 9 is 90, but there are 2 identical permutations for the 2 electrons. Therefore, we have 90 over 2, 45 microstates. Now in this table, we will just look at the sum of the m sub l values of the 2 d electrons. When we have a d electron, the lowercase m sub l can be from -2, -1, 0 to 1 and 2. So we have this 5 values for the first electron, this 5 values for the second electron, and we will sum up the m sub l values for the 2 electrons. Let's look at this cell. -2, -2. So together it's -4. And because these 2 electrons both have a value of m sub l being -2, -2, they must have different spin quantum number. Therefore, they have to be 1 alpha and 1 beta. Only 1 microstate here. So you can see just -4 over here with just a single occurrence. This means, well, the total m sub l is -4. And we can only have 1 microstate with such a value. Now, look at this cell. You see -3, -3, -3, -3. Why is that? Well, over here we see m sub l for 1 electron is -2. For the other electron it's -1. So look, this m sub l values are different. What does that mean? That means, well, their spin numbers can be the same. They can also be different. Now we have 4 different situations. We can have alpha alpha, beta beta. We can have alpha beta plus beta alpha. We can have alpha beta minus beta alpha. So this is the singlet state. And these 3 together is a triplet state. A total of 4 arrangements or 4 microstates. Since we have 4 different microstates, each with a sum of m sub l being -3. So I'm writing -3 4 times. Now let's look at this cell. -1, -1. Same m sub l. Therefore, the spin must be different. We have only 1 possible microstate over here, which is just 1 alpha, 1 beta, both occupying this m sub l orbital. So again, you see the trend. If the value of m sub l of 1 electron is different from m sub l value of another electron, we have 4 options or 4 microstates. Alright, like those cells in the lower triangle. What if the m sub l of 1 electron is the same as m sub l of the other electron? Then you have to have 2 different spin numbers. That means the 2 electrons must be paired with 1 alpha and 1 beta. Therefore, there's only 1 microstate in the diagonal cells. Alright, again, if m sub l is 2 for 1 electron and also 2 for the other electron, well, these 2 electrons must have different spins, alpha and beta. Now we have actually a total of 45 numbers entered. So 4, 4, 4, 4, 4, 4, 4, 4, 4, 4, that's 40. And then 1, 2, 3, 4, 5, 45. 45 microstates have been specified in this table. Now we're going to group those 45 microstates into atomic terms. First, let's look at all those numbers in red. If you look at those numbers in red, they correspond to, well, m sub s equals 0. So it's just alpha beta minus beta alpha, the singlet. Singlet spin, okay? They are all singlet spin. The spin multiplicity is just 1. And now let's look at m sub l, the sum of the individual values of lowercase m sub l of both electrons. It can be -4, -3, -2, -1, 0, 1, 2, 3, 4. So now we have a series. this M sub L can be from -4 to 4. What does that mean? That means L is 4. Now let's look at M sub S. In all cases, M sub S is 0. It's the singlet state. And then the atomic term is 1G. G means L is equal to 4. And the 1 here, that means a spin singlet. 2s plus 1 is 1, so s is 0, and it does make sense over here. M sub s is just 0. It has to be the singlet state. Okay, we assigned a total of 9 microstates to the 1G atomic term. Now we have 45 minus 9, 36 microstates left in the table. So we have 36 numbers in this table. We will further group those microstates. Now let's look at the numbers in yellow. We have 21 numbers in yellow. You can see over here we have 3 identical values, -3, -3, -3. So that means we have a triplet here. The spin quantum number can be -1, 0, and 1. What about M sub L? Well, it can be -3, -2, -1, 0, 1, 2, 3. So we have a series numbers for M sub L from -3 to 3. How about MS? From -1 to 0 to 1. We have a spin multiplicity of 3. You see 3 numbers in each cell. And we have a angular momentum multiplicity of 7 because, well, L is 3. So M sub L can be -3, -2, -1, 0, 1, 2, 3. 7 times 3. We have 21 microstates that correspond to the 21 numbers highlighted in yellow. And they belong to the 3F atomic term. So when L is 3, the symbol is F. And over here we can see M sub S can adopt 3 different values. So the spin multiplicity is 3. And then we further remove those microstates assigned to the 3F atomic term. Now we have 15 microstates left. This 15. And by looking at this 15, well, actually, if you are familiar with the P2 microstates, 15 microstates in P2, so they can be just assigned similarly. It's just 1S, 1D, and 3P. But still, let's work on it. First, let's look at those green numbers. -2, -1, 0, 1, and 2. Alright, and those are the singlets. Alright, so M sub L is from -2, -0, -1, 0, 1, 2. And M sub S can only be 0 for the singlet spin. And we have this 1D atomic term done. And after we remove these 5 green numbers, we will have a total of 10 microstates left. We have only 10 microstates left in this table. Now let's look at the 9 numbers in blue. So 1, 2, 3, 1, 2, 3, 1, 2, 3. That means we have a spin quantum number of -1, 0, and 1 over here. M sub L can be -1 in this cell, 0 in this cell, and 1 in this cell. We have a series M sub L values from -1, 0 to 1. And also M sub S is -1, 0 to 1. So this is a triplet spin. Alright, so that's why we have 9 microstates assigned to the 3P atomic term. We look at the 3P, L is 1, S is 1. When L is 1, M sub L can be -1, 0, and 1. When S is 1, M sub S can be -1, 0, and 1. So we assign this 9 microstates to the 3P atomic term. Finally, there's a 1 number left, which is in purple. So if you look at this number, M sub L is 0 plus 0, which is 0. And we see only 1 0 here, 1 occurrence of 0 here. That means we have a singlet spin. S has to be 0. And then we have the final atomic term, which is just 1S. So when you see this 1S, this S means L is 0, M sub L can only be 0. When you see this 1, that means 2 times the spin quantum number S plus 1 is 1, S is 0, M sub S can only be 0. there's only one option for the spin. Again, this 0 corresponds to the 1s atomic term. The 9 numbers in blue belong to the 3p atomic term. So now we group all 45 microstates into the 5 atomic terms. The red ones, there are 9 numbers in red. It's just 1G. 21 numbers in yellow. That's 3F. We have 5 numbers in green, 1D. 9 numbers in blue, 3P. 1 number at last in purple, that's just 1S. Again, we can just use this table to derive the atomic term symbols for the D2 electron configuration. Let's review this. We have 45 numbers in this table that correspond to 45 microstates. And over here, if you look at this cell, that means the 2 electrons both have a m sub L equals -2. So the sum is -4. And because these 2 electrons have the same value of m sub L, they must have a different spin. So it's going to be a singlet. And that's why I have this -4 appearing only once in this cell, a singlet. What if the m sub L values for the 2 electrons are different? And then we can have 4 different spin scenarios: alpha alpha, alpha beta plus beta alpha, beta beta, alpha beta minus beta alpha. 4 options. The first 3 are the triplet spin. The last one is a singlet spin. So we have 4 numbers here, 4 numbers here in the lower triangle. In the lower triangle, the 2 values of m sub L are different. In the diagonal, the m sub L values are the same. So you have only one possible spin state, which is a singlet. And in the lower triangle, you have a triplet plus a singlet. So 4 options regarding the spin. So you have this -3 appearing 4 times, -2 appearing 4 times, 4 times. This number also 4 times. Okay, and in total you can count. We have 45 numbers in this table, and then we group this 9 red numbers to 1G, 21 numbers in yellow to 3F, 5 green numbers in 1D, and 9 numbers in blue to 3P. Finally, this number left in 1S. Similarly, if you are looking at the F2 electron configuration, it's actually fairly easy. You can just imagine we need to have a bigger table than this. This is 5 by 5 table. For this F2 electron configuration, well, we need a 7 by 7 table. We need to have this m sub L from -3, -2, -1, 0 to 1, 2, 3. And over here, we need to have values from -3 to +3. So we need a 7 by 7 table. And we also will have like diagonal cells and lower triangle cells. And we fill them up and then group them into the atomic terms. And you will see we just need to have 2 additional atomic terms. So remember, for this D2 we have 1G, right? So we have 1G, 3F, 1D, 3P1s. It's just beyond 1G. You need a letter H. H is after G. You need a H, and then you need a spin multiplicity of 3. And then after H it's I, so you need 1I. So you just need to write out 2 more atomic terms. After G it's H and I. And then you can see the trend over here. It's 1, 3, 1, 3, 1, 3, 1. So really you just need to imagine we just need to have 2 more columns, 2 more rows. They also have similar numbers like this. It's just, if you have F2 electron configuration, it starts with -3 and -3. So you will have at most -6 in the diagonal. -6, -2, -6, -4, -2, 0, 2, 4, 6 in the diagonal. and then you have off diagonal triangle. So just because of that, you will get additional atomic terms such as 3H and 1I. And also we can easily determine G2. We just need 2 more atomic terms, 3K and 1L. Know that we know it's HIJKL, but J is skipped just because there's no corresponding letter J in the Greek alphabet. So usually we just look at the letters in alphabetic order after SPDF. So first SPDF, and then alphabetic order. That means we have G, H, I, and then skip J, and then K and L. And then if you look at the spin multiplicity, it's going to be 1, 3, 1, 3, 1, 3, 1, 3, 1. Alternately, due to the arrangement of this kind of table.